Hello, my name is John Mad Dog Call, and I'm the board chair of the Linux Professional Institute. My talk today is how to get a better education for a lifetime of learning and to maximize your career. For those of you who do not know me, I've been in the computer industry since 1969. I've had a wide variety of different jobs for a wide variety of different companies. I have been a university educator, which makes me think that I may be qualified to give this talk. Most of all, I like to think of myself as pragmatic. I try and get the job done. What is a university education? A university education is created by the development of a curriculum to teach a particular subject. Then, once that curriculum has been developed, they create coursework to teach that curriculum, and finally tests to certify that the students have learned that curriculum. In developing a curriculum, you have to determine the needs of society and industry for the knowledge of how to do a particular job. To do that, the university talks with industry leaders and others, maybe some societies like the IEEE, the Institute of Electrical Engineers, and the ACM, the Association of Computing Machinery. These two groups have actually created several different curriculums for several different topics, such as computer engineering, information science, computer science, and others. They publish these freely in PDF form, and they're quite literally a thick book of information. Out of this, they create courses with course requirements. What type of prerequisites are needed for each course? What do you need to know before you try and take the course? What is the proper order to teach the courses in? What is the title of each course in the abstracts so the students know what they're supposed to be learning and how they should use that for each course? Then they review that curriculum with the certification agencies that oversee this type of training for universities. Once they've developed a curriculum, they have to develop coursework for the curriculum. For each course, you have to have textbooks. You have maybe magazine articles to show students, or internet articles, or blogs. You would want the students to do projects to better learn the material and to also show the teacher that they understand what they're learning. You need to have teaching materials, presentations, videos, slides, all sorts of things. And finally, perhaps some sample tests to allow the students to take the tests and see, do they know the information? Are they missing something? You need to certify later that the students have learned. And some of the certification methods are class participation. Do the students participate in class, ask questions, and make observations? They have projects that they work on to better learn the information. And then they finally, of course, take tests. Now, the interesting thing about tests is they point in both directions. Have the students learned the information? Or maybe the instructors haven't been teaching it well enough. So if one student flunks a class or flunks a test or does poorly in a test, then the instructor might say the student didn't study or the student wasn't able to absorb the information. But if many of the students take the test and flunk or do poorly, then the instructor might say that perhaps I didn't teach it well enough, or perhaps the test was not written well enough. So the tests can point in both directions, to students who do not understand the material and to instructors who don't teach it in the proper way. Then there are certification agencies that periodically come into the university or into the department and review the curricula of that university. They want to see what the students have been learning. They want to see sample tests and sample work from the students. And if they feel that the university is teaching the information properly, then they will certify that particular test or that particular curriculum or the university itself. Now, there's a big difference between grade schools and universities. In grade schools, if the information does not come out of the teacher's mouth, it's not going to be on the test. And there's many students who have gone all the way through grade school without even opening a book, counting on what the teacher is going to say in class. However, universities are not like that. The first thing a university professor will tell you is, I don't have the time to teach you all this information. So here is your textbook. Here's the places on the internet to look. You can talk with your fellow students. You can talk with recitation teachers. You can ask me questions, and I'm happy to answer them. But you have to do the learning. And universities do not prepare you for a job. You're not going to go to the university to learn how to use a particular product or a particular piece of software. They teach you how to learn for yourself. And that's why you don't have to go back to a university after 40 or 50 years and get another degree or redo your degree, because they teach you how to learn for yourself. And so they expect that you're going to be learning over time. Things are much different today than when I learned computer programming back in 1969. You know, we didn't have a network. We didn't have security issues. We didn't have graphics and things like that. All of those things came about since I left my undergraduate university degree. However, they taught me how to learn for myself, and that is what I still keep doing. So if you look down the different degrees that a university offers, your bachelor's degree, that teaches you how to learn. Your master's degrees teach you how to do research or how to look deeper into a particular area. The master's degree can also be used to change direction. Maybe you had a bachelor's in electrical engineering, but you want to get a master's degree in electrical engineering to further the depth of knowledge. You could also get a master's degree in computer science. Or you could get a master's degree in business administration, a completely different subject. That's okay. PhDs are the culmination of all of this education. PhDs help to advance the knowledge of humankind through a PhD thesis or a PhD study. They prove the events of the thesis. You have to prove it. And after you've proven it, then it becomes part of the knowledge. We even have a term, because PhD theses are very difficult to do. Sometimes the students chews off too much information. They cannot prove it in their own lifetime. So we have a phrase, PhD ABT. They've finished all the coursework, so it is now a PhD all but thesis. Now, in the first 6 months to a year after you get out of university, you're going to learn a lot. As I said before, a professor doesn't have the time to teach you everything. And certainly, in 3 to 4 contact hours a week or 30 contact hours a term, you're not going to have the same amount of time as working a subject for 40 hours or 50 hours a week with people who have made this their life's work. You're going to be learning how to use the company's tools, the company's software, the company's hardware. You're going to learn how to work with the company. This is what you're going to be learning in that first 6 months to a year out of university. And because of this, I heartily recommend a university that has what we call a cooperative education program. This is where you go to school for 6 months, you work for 6 months, go back to school for 6 months, or so forth. I had 1.5 years of practical experience, even though it took me 5 years to get my undergraduate degree, because I did cooperative education. And it was because of cooperative education that I actually changed from being an electrical engineer to being a data scientist or data programmer, computer scientist. We didn't have computer science degrees back then. We only had computer black magic. So what should you be learning while you're at university? You should be learning principles behind things and not products. Don't learn Oracle database or Cisco networking. Learn how a relational database or an object-oriented database or a flat database works. And then you can look at Oracle as an example of these. But there's also MySQL, there's Postgres, there's all these different databases out there, and even data structures that you should be learning, not a product. This will allow you to keep learning for a lifetime. once you've learned the basics and the principles behind it. You should also be studying up and down the scale. There's a lot of people who think that Java is enough. Java is the only language you need. And I believe that you should learn multiple languages, and you should also learn things like machine language. I don't care what machine language you learn. I don't care what architecture you learn, as long as you learn a little bit about how the machine actually works. And once you've done that, then as new architectures and new machines come along, you can apply what you've learned to them. New concepts and new ideas are easier to understand if you actually know the level of machine and even microcode level in the architecture. Likewise, programming is not enough. Just being able to write a program is not enough. You need to know logic and science behind it. You need to know the computer algorithms. What is the best algorithm to use in a particular situation? And you need to know the engineering behind it. So another thing to talk about is the difference between closed source versus open source in the practical world. Closed source software teaches you how to use the software to solve a particular problem. Problems are what we use computers for. If we didn't have computers problems, then computers would be a little bit useless. So, closed source software will teach you how to solve those problems, but they don't teach you how the software solves those problems. And you can't fix the software or make it better for those particular problems. Open source software not only teaches you how the software solves the problem, or how to use the software to solve the problem, but it also teaches you how the software solves your problem. You can look at the source code for the software. You can see how it solves the problem. And you can also make the software better if you wish in solving that problem. You can find the source code for the software. You can look at the bug fixes and stuff that people are working on, and maybe you can be the person who fixes one of those bugs or extends the software in the case that in the way that you want to see it improved. Free software also extends these to the end users. Open source is great for developers and companies that want to develop software and sell a product, but the end user is still not guaranteed access to the changes that the developer made. And so, free software allows even end users to be able to contribute to the software. There's other problems with closed source, particularly in an educational situation. There's tricky licensing. A lot of the vendors of these closed source programs will give student licenses to the students, but those licenses have a lot of caveats to them, that the student may not be able to use the software on their laptop to solve a problem for a paying customer. Free software does not have these problems. You can use the software for any reason, teaching or, doing real work. But the term free and open source software, hardware, and culture is not just about GNU Linux. There are different operating systems out there that are all open source or free software, like FreeDOS, which is a MS-DOS compatible package that can run MS-DOS binaries on an Intel platform or under an emulator type of version. You can see how the software works or interacts with the operating system. There's NetBSD, FreeBSD, and OpenBSD as part of the Berkeley software distribution package. There's TinyOS, which is a very tiny operating system for Internet of Things. Carnegie Mellon University's Mach microkernel is very famous to see how a microkernel works. And Minix is also a microkernel for educational use. And there's many more different operating systems you can look at. But it's not just operating systems either. If you go out to SourceForge or GitHub or GitLab, you're going to find tens of thousands of projects for databases of all types, for video creation, capture, and playback, for audio creation, capture, and playback, for geographical information systems, for Internet of Things. There's over 400,000 projects with 2.6 million developers working on them. But it's not just about software. It's also about open hardware. And there are complete working designs of systems out there. BeagleBoard and Olimex are two companies that make a lot of their designs completely open and completely free. Circuit designs, building materials, printed circuit board layout, and other things, so that you can actually build your own board if you wanted to. Field programmable gate arrays are another example of opening software and opening hardware that they move closer and closer to being truly open every day. Field programmable gate arrays can be used as accelerators in your system to be able to do things fast and also to offload the main CPU. RISC-V is an effort of many universities and industrial partners coming together for a new hardware architecture that is completely open. But we also have open culture. It's not software, it's not hardware, but instead it's text or graphics or music or all the different types of things that people can do but are copyrighted. You now have a license to allow you to freely license these things to other people for whatever project you want to do. In fact, if you look at the bottom of my slides, there's a little rectangle there. That is actually a Creative Commons license. It tells you can distribute this talk freely, but if you want to modify it, you have to come back to me for a different license. Now, you can also do learning on your own. So what you do is you go to a university site, you find the curriculum that they've posted, you see what the courses are that they're teaching. You can then go out and find the books and the internet courses and all the things to gather together the information to learn that subject. Then you can study on your own using free and open source software, hardware, and culture. You can even use old hardware that's been cast off because it doesn't work as well for the modern day operating systems. And you can use virtual machines to run different operating systems, different programs and stuff if you don't have that particular architecture. Finally, after you've done all of your study, you can take certifications and have a certificate which says you know what you know. Now, a lot of these certifications or certificates can be on a language or a particular distribution like Red Hat or SUSE. However, they can also be generalized, and we're working very hard to do that to remain vendor and distribution neutral at Linux, LPI. Finally, I want to talk a little bit about the studying of products instead of principles. Nortel Networks Corporation was the second largest networking company in the world. They've been around for a long time, 1895 to 2013. In 2013, there was a huge upswing in Nortel Networks went belly up, bankrupt. And in a very short period of time, all the people's certifications that they got through Nortel's products were worthless. So if you're looking for a certification, you want to pick a good certification agency that does the certification effort the right way. And you want to have them developing their objectives from within industry and with input of industry, so that when you go out after getting the certification, you easily find a good job. You want to make sure that they periodically update those objectives to meet new industry needs. And a good example of this, and I must admit this because I'm the board chairman of the Linux Professional Institute, is the LPI security certification that is done. And there's a URL for that. You can look at it, you can see the objectives, and you can then study that. When you're finished studying that, you can then take the test and get the certification. Now, certifications are only part of this. You also want to work on real-life projects. You want to be able to pick out a project that you are passionate about. And you want to start with bug fixes, fixing the bugs, looking at their bug list, making the bug fixes and submitting that to the team. They may accept them right away, or they may say, gee, if you rewrote this to blend in better with the code we already have, that would be much better. After you fix some bugs, then you can go on to implementing small new features that are needed that they don't have time to implement. And after a while, maybe they will invite you to join their core team. So in all this process, you save emails where they praised you. You save samples of your code that you've written so that you can show this to your potential employers. Closed source doesn't reveal the name of their engineers that created it. And so open source would allow you to show all this information to your potential employer. You can get recommendations from the people in the team and even from your peers. You can write blog articles about what you're doing. You can show samples of your code in your articles and in your presentations. Sometimes you'll be invited to a conference that's either locally or nationally or internationally, which gives you a chance for exposure. There's also more ways to get started. You could do gratis works for nonprofits. Maybe the church needs some work done in a database or some type of networking, or a nonprofit organization. And you can get letters of recommendation from them after you've finished. You can also mentor or teach a subject to somebody else. When you're just learning the subject, you may think, well, the professor will never ask about this particular part of it. I can ignore that, or maybe I'll only get a 90 on the test instead of 100, but I'll still pass. But however, when you teach it, you're not allowed to do that, and you have to learn it really well. I took compiler theory once in undergraduate and once in graduate degree, and there were still parts of it that I didn't quite understand. But when I had to teach it for the first time at Hartford State Technical College, I had to learn it 100%, absolute. And still, 20 years later, I can still remember how to design and build a compiler. You can start a cooperative with your friends, gather together people who want to go into business with you. Start a business plan. Make sure you can make money. Make sure your idea is competitive and sustainable. But don't be afraid to fail. Many people have failed. In fact, in Silicon Valley, there are people who lend out money who won't lend it to people who haven't failed at least twice. Failure is part of success. Remember, I am an old fart. I have been programming and in computers for over 60 years. And someday you will be an old fart. And maybe you can mentor other people and help them move forward. But to do that, you always have to keep learning. You always have to keep learning. And that is what your undergraduate degree teaches you. Certifications can help you keep on track. They can also help you learn new things in the industry. And certifications can help you change direction if you want to go off in some other way. All of that having been said, I've never regretted the years I spent at Drexel University. I started off as an electrical engineering student. I transitioned into commerce and engineering that was half business and half engineering with a computer minor, a minor in this weird thing this weird thing known as computing. And I had a professor tell me, John, you will never earn a living as a professional programmer. And after 60 years, I'm still wondering if he was correct. I've met many people at the university that have maintained my friendship over years. But university is not the only way to learn. You can learn on your own. But remember that you are in control. You can decide what you want to do. You can decide what you want to learn. Never give up. A lot of times I go to trade shows and I will have people walk up to me. I went to CeBIT a couple of years ago, and people walked up to me, and one man said, I listened to you talk about open source 5 years ago, and today I'm the head of my department. Another man walked up to me and said, I listened to you 10 years ago about free and open source, and now I'm the chief technical officer of my company. I had a third person walk up to me and say, I listened to you 15 years ago, and now I own my own company, and I employ 60 people, and we make a great product, and I thank you. And this makes me feel very good, because I have helped these people have a better life through the use of free and open source software. So with that, I will end my talk. I thank you very much for listening, and I will open it up to questions.